In part 3 we have a look at the dynamic response, the artifacts, non-ideal perceptual response, the complex impedance load, loudspeakers, and the limitations of testing with continuous tones. From the above, it should be clear that it's absolutely necessary to determine the dynamic responses of an amplifier as realistically as possible, either by calculation or by measurement. The latter is rather difficult because we're usually talking about very small effects. So the lowest number of assumptions is crucial for the calculations to make sense, and the linear Fourier theory does not suffice boundary conditions, as has been noted by Coulomb among others. Yeah? So, but we need a non-linear description, and it can be achieved using numerical techniques like those applied for solving non-linear differential equations. And the method is described in detail in the paper in the website, and you can find it there with also more proof that it really makes sense what you are doing. But for the sake of clarity, here I only present results. It produces the output signal of a modeled amplifier. Basically, it consists of the operating lines of the different stages and the low-pass filter, a given input signal. And in order to determine the effect of the nonlinear properties, the same input signal is again used, and then all the operating lines are taken straight. You can do it in a computer, it cannot be done in reality. When you compare the two, you see the results of the non-ideal behavior of the amplifier. And we'll show the responses to a 3-cycle tone burst, but this will be calculated. But it's not limited to this. You can basically use any signal of any length. If you want to have a music signal of, say, 10 seconds, it can be done. That's not the problem. But in order to make things clear, I'll use a 3-cycle tone burst in this case. This is the output of a such a 3-tone burst. You see that it consists of a DC component and an AC component, and the AC component is mostly consisted of the second harmonic. This is the AC component, and it's mostly second harmonic, as you can see, not fully because the amplitude is not constant, so there is a bit more to it, but it's mainly second harmonic. And this is the DC component, which is basically the envelope of the signal. Well, when I do this again, but now with the different conditions, I use a color frequency of 2.5 kHz and the 3-cycle tone burst has a frequency of 2 kHz. I get this result, and at 10 kHz I get this. And as you can clearly see, there's quite a strong effect of the frequency. So we see that they increase above the color frequency of the low-pass filter of mu, that was 2.5 kHz, and it's caused by the decrease of the feedback factor. The question is whether this decrease can fully be explained by the increase of the artifacts. Well, I've done the calculation. This is frequency, as usual on a log scale. This is the vertical scale, this is distortion plus artifacts, but also on a log scale, so this is a factor of 10, don't underestimate it. We see that if we play correction for the decrease of the open loop gain, which is basically nothing but the inverse of the low-pass filter characteristic, we see that the distortion and artifact increase goes far more rapidly. So the operating points shifted to the nonlinear amplification stages, and it increases rapidly with the increasing strength of the input signal. We've seen that before, and this is roughly quadratic. So it is to be expected that the artifact will also increase more than proportional in the signal space. And this can either be shown or disproved with the 3-cycle tone burst with a triangular envelope. The tone bursts I've discussed so far have a rectangular envelope, but now we use a triangular envelope, so it increases and then decreases again. And if it would be, say, the artifact and the distortion would be similar, then the distortion should fit into a triangular fit. Well, we fitted this triangle to the highest point here, and we see that with decreasing amplitude, that it goes far faster down, which means that the artifacts relatively go up a lot faster. And this is again one of the root causes for the call of headroom. So we see that they increase above the cutoff frequency of mu, more rapid than the increase of mu, and due to the decrease of mu, the differential input increases, and this will cause a stronger rise of the artifacts. So they're basically a must to avoid. But they also include, and that's something we should emphasize, lower frequencies. It will always occur. And that has severe consequences for the perception, because I've again this 10 kilohertz signal plot here again, and now you can do a Fourier analysis of that signal, and then you see here a 20 kilohertz signal, which is the second harmonic, 10 kilohertz, but also a low frequency peak, which is about twice as large, more than twice as large as the second harmonic. Well, this one probably you'll have very difficult to hear, but these low frequencies end up in the very audible audio band. So the signal generates artifacts which are very clearly located in our hearing. So the second harmonic is there, and it's obvious, but the envelope is also there, and this one is perceptually very distorting. And by high frequency radiation, which comes into the electronics, and by radio, telephones, also artifacts arise by detection, and those end up also up in the audio band. So you can reduce these effects by limiting the closed loop bandwidth to, say, 200 kilohertz. But this will limit the feedback factor at the same time. So what's the effect of the distortion as a function of frequency? Well, if I use a low cutoff frequency and a high feedback factor, I get this response for the distortion and artifacts. Note again the logarithmic scale. And with a high cutoff frequency and a low feedback factor, I get this. So at the low frequencies, I get a lower distortion, but it very rapidly increases with frequency. And with a high cutoff frequency, I have a far lower level at higher frequencies. And I think that, I'm pretty sure that this will perceptually far more acceptable than this. So how can we suppress these artifacts? So let's take an example. Yeah, we want to keep a feedback factor below 20 kilohertz constant, and we'll limit the closed loop bandwidth to 200 kilohertz during a first order filter. And this will limit the maximum feedback factor, and that's the suppression misery, to approximately 10 times, or 20 dB. So 20 dB is still something worthwhile, I think, so I'm not going to put it at garbage, but it's only valid for the last amplification stage. Of course, that one is which has to process the power, so it might be still very attractive. But for the other stages, a different approach design is required. So we have to find either alternatives for the transistor or the transistor amplification stages. This can be done. We apply it. This is the distortion of an ordinary single transistor amplification stage. So it's a single sine wave. And when you look at the difference between the input and the output, you get this. And with the alternative amplification stage, you get this. And I didn't manipulate the results. The scales are the same from minus 120 to plus 80, minus 120 to plus 80, but you can see it is significantly less. So this is one of the major reasons why all our equipment is built up using discrete components, because then we can get those amplification stages as we want them. Then there is the influence of the power supply. The perceived quality of an amplifier is also determined by the quality of its power supply. When the power supply voltages are not constant, the operating point of the individual amplification stages will shift. And we've seen that the shift of the operating point of the individual amplification stages generates artifacts which are highly undesirable. So how can it vary? Well, due to variations of the power gate voltage, the current demand from the amplifier's buffer capacitors, current variations by the amplification stages, and that sort of stuff. Feedback theory predicts that also in this case, the misery introduced is reduced by a factor of mu0 beta. But it's different for each amplification stage. So it's only valid for the last stage. And the feedback factor is limited, as we've seen before. Let's say for ease of discussion 20 dB, when only above discussed aspects are taken into account. So the suppression of the misery introduced by the power supply is limited anyway. Stabilization of the power supply voltage is a necessity for optimization of the options to improve the amplifier. Regulated power supplies also prevent that all kinds of misery and undesirable signals sneak in via the power supply rails. So only well-regulated power supplies can be regarded as time invariant. So it's standard within our company. And the other Dutch expression is to prevent is better than to cure. In that respect is an interesting anecdote. It's quite a while back, but still it's as valid as could be. Yeah. We tested an amplifier. Its specifications were actually quite good, but it didn't sound well. And during testing with continuous sine waves, it showed that it did perform up to its specifications, which was quite a surprise actually. But the amplifier immediately showed its limitation when the testing was done with tone bursts, because the power supply was not able to cope with the variations in the current. So the power supply voltage varied strongly with the strength of the input signal, and this artifact showed up at the output, and which is the cause for the low perceived quality. The amplifier no good? Well, the amplifier itself actually is quite okay. Its power supply is the problem. An improvement of the amplifier itself is useless. Replacing it with the power supply, however, on the other hand, is very effective. So when the power supply is improved, the amplifier, however, will still behave the same for continuous signals. It just sounds way better. So same amplifier, strongly different perceptual quality. Blaming the amplifier or feedback is therefore jumping to conclusions, as replacement of the power supply does not change a single thing to the amplifier or its feedback. But you can imagine that when your power supply is limiting factor, that you also need headroom, because when you get more power, the effects of the power supply are more severe. And for the purists, it's very well possible that an amplifier with feedback sounds better than one without feedback. How come? Well, the quality of the power supply of the amplifier without feedback has insufficient quality. All kinds of artifacts are generated which can be qualified as highly undesirable. It's given too little attention, but no apparatus is better than its power supply. Then why are power supplies often so insufficient? Well, it's easy to see. A bad power supply, its specifications are not worse compared to a good power supply. So this is an ideal item for cost savings. Bookkeepers are jubilant. Now, loaded with a complex impedance, a loudspeaker is in general not a purely ohmic load. Voltage and current are in the phase, and this is a courtesy of stereophile. The impedance measurement of a loudspeaker, the drawn line is the modulus of the impedance, and it varies between, say, a little more than 3 ohms to up to almost 15 ohms. And the dotted line, if you use this scale, is also quite varying, and it varies between, let's say, -30 to +45 degrees. Whereas a resistor has a constant value, say 8 ohms, or in this case might be 4 ohms, and the phase is 0 for all frequencies. So there's quite a difference in the impedance, and because this phase shift, we call this complex, because you can describe it with complex numbers. And when you look at what the amplifier has to do, you see within the ellipsis that there is an opposite polarity between voltage and current. And it happens here. And what are the consequences for the amplifier? Well, when they have opposite polarities, conflicting demands are imposed on the amplifier, especially on the power stage. The positive output voltage, the upper ambient transistor needs to conduct, but when simultaneously the current is negative, the lower PNP transistor needs to conduct. I can illustrate it here. This is very simple. This is the mu, the feedback circuit, this control circuit for the power stage. And in order to get a positive output voltage, this transistor needs to be open, but in order to drain the negative current, this one has to be opened. Whereas with an ordinary AB power amplifier, this cannot be done. It's designed for ohmic loads, when the voltage currents are always in phase, with the same polarity, and only one of the two power transistors can be made to conduct. So when you want to try to conduct both, you get in conflict. And it will have audible consequences, and the circuitry cannot put both transistors in conduction. And this gives rise to enhancement of the crossover distortion, which can only be marginally expressed by feedback. And why? Well, the crossover distortion is short compared to the cycle time. It only occurs close to the zero crossing, and it generates mostly high harmonics, which the feedback is not very effective, because the mu drops. And this is an illustration of it. This is the output signal, and we see that there's crossover distortion near the zero within the ellipsis. And because this time is short compared to the cycle time, this represents very high harmonics of the sine itself. And when you do an approximated calculation, then you get this result, again at the vertical scale, which is logarithmic. This is the number of harmonics. It goes very, very high, up to the 50th. I'm done here, and then I stop. It can even go further. And then you see that they increase with the harmonic number. And say, only from above the 40 becomes more or less constant. So you see two effects there. Lots of very high harmonics, and they increase with frequency, which means that the suppression gets worse and worse in this area. So it's from a perception point of view, dramatic. So that can be another reason for the difference between measured and perceived results with loudspeakers. How well an amplifier is able to cope with it, and how well the loudspeaker behaves is another matter. So in order to get this clear, you need to make the measurements with realistic loads and not a resistor. Note that Class A amplifiers do not have this problem, because the power transistors carry the maximum current all the time. The negative current is basically nothing different but a smaller positive current. But we all know the price. You get a very bloody hot amplifier, shorter living, and get a high electricity bill. So impedance compensation is an excellent way to change the loudspeaker impedance to close as ohmic as possible. So you change it such that the whole thing starts to behave like a resistor. And there's a nice YouTube, also made by Hepta, where you can watch how that can be done. But there's also at the website a paper on it that you can read. But it certainly improves the sonic quality of amplifiers, and Hepta Design Audio applies this, which means that you can have the improvement without changing over to a Class A amplifier. And you can find on our website the complete publication. Well, there are a number of effects which cannot be detected with single-tone continuous signals. We noticed at the beginning from different authors that there are clear differences and inconsistencies between measurements and perceived results. Can we now understand these differences, where they come from, and how this can be improved? What can we learn from it? Well, we've identified a number of problems with amplifiers with feedback. And can these be uncovered with the standard measurements and tests? Not quite. Which cannot be detected. And they're not all, but some important ones. The shifting operating point of the individual amplification stages cannot be detected. The charge changes of the cutoff capacitor of the low-pass filter due to the shifting of the operating points cannot be detected. Low-frequency artifacts in the detection of the envelope cannot be detected. Demodulation of high-frequency signals cannot be detected. Time smear introduced by the amplifier, no way. A variation of the power supply voltage you cannot detect either, which makes them so attractive for bookkeepers. So there are a number of artifacts that cannot be detected by the common test techniques. Therefore, it's very well possible that two different amplifiers give equally good results on the measurement bench, but show significant perceptual results. The unpleasant aspect is that many developers just use the bench readings as a result for leading the development, but neglect the perceptual irritating artifact and sometimes even enhance those, which ends then by